Okay, thank you very much. So yes, Gabby's asked me to talk about terminology and fundamentals on wetlands. I should explain I come from a process engineering background about designing and adapting wastewater treatment technology, and so that's kind of the angle I'm going to take here. And then I'm going to show a little bit of data on some nanoparticle work we did, actually linked to the project Greg was involved in with us, that will show some colloidal banding of nanoparticles. Not across wetlands, unfortunately, but I thought it shows some relevance to what I want to talk about. So, my very non-wetland community definition of a wetland is that it involves land, water, air and plants. And so as long as it has those four components in it, I can call it a wetland. Then I have loads of variations around that, but I do need those four components really to call it. And it's then about the relative significance of the soil base or the solid base, the plant base, the water phase, and then the interactions with the atmosphere. So, if I think about the systems, I can describe them in a number of components that when I'm then thinking about the function of wetlands and how I might influence that, these are the things I need to talk about. So, it's got to be in some sort of container, be it a hole I've dug or a constructed vessel, and it will be either lined or not lined. So if I'm doing it as a treatment technology and I'm constructing the wetland, then I will tend to line it so that I can control the flow, I can control where the water goes. In the natural systems I would tend to not. There obviously would be no lining unless there's a natural clay lining in the soil structure. It will then contain a solid phase and media, which will either be soil or gravel or sand or some form of particulate. I've of course got plants, a whole range of plants. Again, in our constructed systems we will have some control there, and we will put in specific plants with a belief that they have specific function. And obviously in natural systems it's whatever develops. And then I've got a water level, either below or at the level of the material or above it, and so there are relatively different flow patterns that could occur in the different types of systems. Now I would argue, if I think about all of those four things, I can describe all wetlands. And I can describe all wetlands and understand how things might happen in those wetlands, because it's the relative significance of those four components that influence what happened. So, to skip me not having to make a fool of myself talking about natural wetlands too much, the way I picture them, in the same way that I picture constructed wetlands, I put them into the same bracket as intensive treatment technologies. I believe the same science applies to everything. So the differences are about the hydraulic rates I might see. And so in our natural systems they're generally quite low, and they get more intense when I go to the constructed wetland because I'm starting to control it, and then I'm putting most control in my intensive technologies and I'm pushing the water through far quicker. The same would be true of load for two reasons. One, because the hydraulic load is higher, but also in my natural systems I'm tending to experience lower pollution concentrations. So they're dilute and low hydraulic rate, where I'm going to concentrated and high rate as I go up that chain. However, the big difference is in then control. So in my very intense technology, I'm putting in a reasonable amount of control. There's the minimum amount of variation that I can afford to exist. I go all the way down to the natural wetland, and of course, well, as Greg was saying, sometimes it rains heavily, sometimes it doesn't rain. They are highly variable. So they're low hydraulic loading on average, they're low loaded, but they're highly variable. So probably the more dynamic of all the systems, but the relative significance of the different components changes because of the hydraulics, the load, and the variation. And I think the most obvious area for that would be the role of the plant. And we'd expect the plant to have more influence in the natural wetland systems than it does, and I think has now been shown in the constructed wetland systems. Okay. So I stole some of my slides from Gabby. She made me give the talk. I stole some of her slides. This is then how I can get to all the different types of systems. I don't really want to go through this, but in a bit I will talk about a few of the newer variants, because it's changing the function of treatment wetlands, which means then when we think about nanomaterials going through these systems, there's a whole different set of chemistry and processes going on. So, if I then think about it in general terms, I can have physical, chemical, or biological pathways. All three occur. I think we can sometimes get a bit obsessed with, we look at physical pathways, chemical or biological. In virtually all systems, all will happen. If we're talking about the physical processes, and a lot of traditional wetlands have been dominated by this pathway, it's really about clarification. It's a sedimentation, a settlement system, low flow, the particles settle out under the force of gravity, the media there collects them. There's a bit of biological activity, and we could debate the relative role of that in its design. If we go to the chemical type systems, we're talking about absorption, obviously some gas stripping depending on the chemistry, and in some of the newer type systems, especially around phosphorus, precipitation is becoming a very dominant mechanism in those pieces of technology. And then we've got the biological processes. So this is really the combination of plant and biomass uptake. In the natural systems, probably quite heavily plant oriented. In our constructed treatment wetlands, much more biomass oriented. In our traditional wetlands that tend to be subsurface flow, certainly in the UK, they will be oxygen starved, so will be anoxic or anaerobic. And then if we go to the vertical flow systems that are used for total sewage treatment, we're going aerobic. So we've got a whole range of redox chemistries that could be going on, and biological consortia that could exist in these systems, depending on what I'm trying to use them for. That then gives me a range of ways of trying to change things. Now, when I'm thinking about what will be removed and what are the properties of the things that I'm trying to remove that are important, when I'm thinking about physical, it's quite easy. How big is it? How heavy is it? When I get to chemical, it's not too bad. It's about charge, hydrophobicity, molecular weight. When I get to biology, it all goes to pot a bit. It's very difficult to look at an organic molecule structure and say, oh, this will be easily degraded, this will be slightly less. It doesn't quite fit that pleasant little world for us so much. So there's a little bit more uncertainty there. But then, how do I influence? And I'm going to talk about most of those as we go through, and the relative importance of those design components. One of my underlying messages, I guess, is traditionally a lot of horizontal flow systems tended to have a degree of surface flow on them, not by design but by operation. Now when they're just there for settlement, that's probably not a problem, but now I'm trying to make them a bit more funky. I want them to nitrify, I want them to remove phosphorus. That free surface layer adds significant risk of transport. And so when we're talking about nanomaterials, free surface flow eliminates most of my mechanisms here. So, onto the plant. I have to own up, I'm not particularly pro-plant. I'm a wetland man, not particularly pro-plant, which is, I agree, silly. So the plant will release some oxygen around its root zone. It's how it protects itself from metal toxicity. Now, it's not enough to aerate a wetland, and so it's not going to drive aerobic biological processes if I'm trying to treat sewage, but it is there as part of the plant's protection mechanism. So when I'm looking at uptake of metals into plants, there is already an aerobic protection mechanism there, so when I change certain aspects of that, they're still going to exist. The plant will try to survive in the environment I put it in. So, but it doesn't live for very long, past the depth of the filter, so it's only around the close proximity. So I can get anaerobic, anoxic and aerobic environments, redoxes, across a wetland. Very complex biochemistry. Okay. So this is from Gabby's PhD. I can't remember, that wasn't at Cranfield, it was a little while ago. And it's just to say the point in, this is in a constructed wetland, treating wastewater, and it's just to show that in those sorts of systems, the high loads that we're dealing with, the plant can't, the mass balances just don't hold. The plant material can't be accounting for the metal. It's on the biomass, it's on the media perhaps a little bit, but it's really about the biosolids that are accumulating within the reactor. In our natural wetlands, I think that switches round and we'd see a very different pie chart. Unfortunately, Gabby hasn't done the pie chart for a natural wetland, so we should blame her. So we do a lot of work, me and Gabby, for the UK water companies on treatment wetlands. So that's really where I'm coming from. Now, most of those are horizontal subsurface flow. So they're there to capture solids, remove some organics, denitrify a bit. Although no one's putting them in for denitrification consents. So they're really there for solids. As a consequence, it's not been so critical about water level. They're there for sedimentation. A little bit of water above the media at such a slow rate isn't going to really distort the bed. So it's quite common to help prevent operational problems around weeds growing and other things like that, to just run them a little bit above gravel level. No one pushes it down as they mature and it stays that way. That offers a big route for short-circuiting. Traditional wetlands, these horizontal subsurface flows that we use a lot in the UK, not such an issue. But maybe if I'm now starting to talk about removal of colloidal nanoparticle associated material, well, they don't settle very quickly. So actually, they may pass through this short circuit route. So I need to think about it a bit more. I've been building they've been being built to remove large solids. Not 10 microns, 50 microns, 100 microns, 200 microns. That's what we've been worrying about. Not 400 nanometers, 100 nanometers, 50 nanometers. There's a big difference in what you need for those two clarifications. So we need to think about that when we're thinking about the new variations that are coming around. The other thing we have to think about is our redox chemistry. So I say in the UK we've tended, and in other parts of the world, but in the UK especially, we are almost quite taken by horizontal subsurface flow tertiary wetlands. There's quite a lot of them around. And of course then elsewhere, and we'd see a lot of vertical flow wetlands as secondary wetlands, primary, secondary wetlands for main sewage treatment purposes. Now of course the vertical flow systems, which are intermittent, you flood them, you drain them, are very aerobic. And generally provide enough oxygen. You operate them to make sure enough oxygen is getting into the sewage so that you're driving those aerobic biological processes. Where in my horizontal flow wetlands, there's no real oxygen involved. The very top layer of the water will get some oxygen through mass transfer from the surface, but it's not enough to meet the demand of the biology within the system, so it's going to remain anoxic anaerobic. So just by choice of which flow direction I'm using in my wetland, how I have to think about that in terms of fate of nanomaterials and colloids is going to be very, very different. The sorts of chemical, biological reactions that could occur in those different redox chemistries change the situation quite a lot. Then the other thing is we have to be a little careful not to be overly simplistic. Variation, that seems to be a common theme of the morning. Well, here's some data again from one of Gabby's papers that shows the variation in hydraulic loading rates for seemingly the same piece of kit. So if we're trying to think about what should these units do, and it will be obviously even greater for the natural systems, there is large amounts of variation from one to the other. So we have to be a little careful that we don't oversimplify what's likely to occur. And then what's happening? So we're starting to need to remove ammonia in these beds that were there for solids. So one of the big things that's been happening is people are starting to add air. So a little bit of aeration completely changes the function of the bed. So I've got my traditional one here. I can only get to low ammonias if I treat it at very, very low loading rates. I add modest amount of air, and actually it completely nitrifies. But I have radically changed the conditions within that bed. Also, whilst it's still light, I've changed the mixing pattern. So again, if I'm starting to think about colloids and nanomaterials, even if they're bound a little bit, suddenly I've now got a free surface layer potentially, and I've got some movement, which is obviously a big risk in terms of a short circuit route out. I also, if I over aerate a bit, I could obviously strip some material out into the gas phase, but these are pretty gentle aeration systems. The other one is phosphorus, and probably well, it's quite a lot of the talks actually at the conference is about how do we deal with phosphorus in wetlands. Probably the preferred solution at the moment is to use not gravel, use a different material that provides a reactive process. Generally that means calcium oxide dissolution. So here we've got a number of different materials. Steel slag is the only one that has any impact, but that's because it's the only one with any appreciable quantity of calcium oxide in it. And actually people are using other materials, and we're going to hear talks about them, but generally to make them appropriate, they're all adding calcium oxide to bind them into granules. So calcium oxide is probably the game in town. It dissolves, becomes calcium, releases the hydroxide, the pH shoots up. It's not uncommon for these beds to be at pH 11. And so I quite quickly form precipitate. Now we talk about forming calcium phosphate, but actually we form calcium carbonate with a little bit of phosphate. So now I've got a very different system again. So now I'm thinking about nanoparticles in a wetland, which is actually in very high pHs, with a very high precipitation reaction going on. Unsurprisingly, these beds are very good at removing metals, because they precipitate them all out into the structures of the calcium carbonate. It makes the calcium carbonate worth nothing, but it is actually a good pathway for metal removal. It's not such a good pathway for discharge at pH 11, but that's a slightly different challenge. But again, it's just showing that as we adapt wetland technology to do new jobs, we've got to be careful that we don't forget that when we're thinking about everything else. Great for phosphorus, but is it doing the rest of the things that we relied upon? And of course, at those sorts of pHs, I am now, just through my knowledge of Henry's law, I'm expecting things to just go out into the gas phase. The other thing that we really do need to think about is that wetlands are long-term biosolid storage devices. Actually, even the natural ones will store a lot of sediment. I store sediment for very long periods of time, and it changes. So here's some data, some of the work we're currently doing, which is looking at the risk associated with using iron coagulants to remove phosphorus and then put them onto wetlands and leave them there. And what happens over time is they become, as they get solid loaded, they ultimately become switch from aerobic to anaerobic, or through anoxic to anaerobic. In under anaerobic conditions, then I'm able to use iron reducing bacteria and I suddenly release a load of iron and phosphate. So what was a stored amount of material then becomes available back into the liquid. So not only have I got to think about how are the changes and what happens in terms of fate in removing, I do have a potential re-release source here, which would be quite uncommon in a lot of other type of systems. And so here's some data, and this was a little beaker experiment, just to show that I can, over quite long time periods here, but you know, we put some sludge in a beaker, it takes a while for everything to kick off, but I can start to release phosphorus, I can start to release iron. Now what happens is it's unclear if that, oh, is she about to tell me to stop? It's unclear what happens at the moment to that material. Does it then start to re-precipitate into sort of 200 nanometer, 500 nanometer precipitates? And that bit of knowledge is actually still missing. Yeah, okay. I'll skip dynamics then. So I just wanted to talk a little bit about how that might fit into some of the things we know about nanoparticles. So this is actually some work I think that your team did, Greg, actually linked to us. So as part of a UK-US initiative, Cranfield got the glorious task of making sludge. So we set up 3 complete sewage works at pilot scale: primary, activated sludge; secondary, anaerobic digestion, filter press, to make these biosolids. And in one of those lines we did nothing, we just used sewage, and we have our own sewage, we have a sewage works to play with. We put metal salts in one and we put nanoparticles in the other. And we did nothing, we just kept everything constantly feeding it with new nanomaterial, so it was drip fed in at the concentrations and so forth. From a treatment engineer point of view, it was quite dull, because we weren't varying anything, but from a biosolids generation for the rest of everyone else, it was very important. And one of the key things they found, and I think it's important when we're thinking about how these systems work, depending on the redox routes you take, the transformations change. So no nanoparticles are their native state, as we've said, but they will vary depending on how you treat it. And so as we have very different potential processes in wetlands, depending on what we're asking the wetland to do, we could get very different speciation. Here's some of our data from that experiment to show the sorts of levels we were getting in our cake. So we did quite high concentrations again, so that we could generate material that could be analysed. So this is just really to say we didn't think they were too dissimilar in terms of how much went into the sludge and how much went into the liquid between the ionic metal salt and the nanoparticle. But we must remember they all aggregate. This is actually not the nanoparticles in question, but nanoparticles will aggregate in natural environments because of the ionic balances, the calcium, so forth. So I'm not going to ever have individual nanoparticles in my water. So we did do some colloidal fractionation. So I was told I wasn't allowed to talk about membranes, but I have to here. We used membrane filters to fractionate out the colloidal fraction. So we'd taken off the 450 nanometer fraction with a standard filter. We discarded that and then we analysed subsequent fractions. So, and in this sort of experiment you have to make sure that you only filter half the volume, otherwise you concentrate the material and it becomes a much finer filter. Okay, so we went through all of the things. Now what we're looking at here is, this is the aerobic side, this is the anaerobic side, this is the control, the dissolved metal, the nanoparticle. And all I'm trying to show through this is, if we look at the different fractions, really small to quite big, and I've kept them as kilodaltons because I don't believe in the transference into nanometers. The anaerobe's pretty similar. The control, the metal, the nanoparticle, all roughly happening in the same sort of sections. But if I go to the aerobic, I think the key is that they look different. So actually, the nanoparticles are partitioning differently to the dissolved metals in that colloid set. Now, in the total mass of nanoparticles, it's tiny. But there is difference. There is evidence that they are going into different associated colloid fractions. What that means to wetlands is slightly more distorted. But I thought it would be interesting because actually we've been, not like Greg, we're very lazy, haven't published the data yet, so I thought I'd share a little bit of it. This is where I'm ending. And really the question is, I think we've got to be very careful about saying what's the fate across a wetland, because it captures so many different possible things. We've got to be quite careful that they can be aerobic, they can be anaerobic, they can operate at neutral pHs, they could operate at very elevated pHs, and so forth. So there's a whole mess of different possible pathways that could occur through that bed. So I don't think it's possible to answer the question, what's the fate of nanoparticles through wetlands? I think you can talk about different transformation processes, and you can talk about them by groups of wetland type, but I think there's far too much variation in what could occur to be that grouped. Okay, thank you very much.